Lennard-Jones potential is what we will be studying in this project. And it can be modeled by this equation here, where E total of R is equal to A over R to the 12th minus B over R to the 6th. And R here is the interatomic distance, which is usually represented in nanometers. And E total is usually in electron volts. And A and B are usually just a constant number, and they're sometimes like the -8, -7, but very, very small numbers here on the numerators. And the Lennard-Jones potential, it describes the force and energy between two atoms and their interaction based on distance. And this interaction can be described using two balls or two atoms that start out far apart, and through some force they are moved inward, which is pretty easy to move them in at first. And then they get to some point, and the attractive force becomes very strong, and it becomes even easier to move them closer together. So they're brought all the way closer together until they're at a point where they are touching. So they're at this point, they're touching. And now, at this point, it becomes increasingly harder and harder to move them closer, because the internal forces here are repelling, and it does not want to move together. So they are pushing each other away, and that is basically what the Lennard-Jones potential is saying and showing, and it can be shown in the graphs that we will be showing next. So I just wanted to introduce myself. I presented the last slide, and I will also be presenting this slide. So I just forgot to introduce myself, so I just wanted to let you know who I was. So let's get going here. So the attraction and repulsion, again, is modeled with this equation, where A over R12 is going to be your repulsive term, because that is the positive, right? So let's draw it out. Your graph. Here's your graph. Here's R, and then EV. So we're going to start really, really, really far away, R values, infinitely far, and using this first term, the A over R12, this is positive, so it is going to go up this way towards the positive infinity, and that is going to be your repulsive term. And now the other term is going to be, this negative term will be your attractive term. And that is going to go down towards negative infinity. Okay, and then those two, now this whole equation, when it is put together in one graph, will look like this. We'll have the same setup, and it will look like what is called a Nike function, where it's going to start up where your repulsive term will take over, repulsion, 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 and then it's going to hit 0, where it's at equilibrium, and then attraction will take over. And you'll have attraction take over, and then you'll see the Nike, and then you'll go back to 0, which I could draw it a little bit better here. So I'll do it again. So you'll have repulsion, 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 equilibrium, down towards attraction. It's going to attract, and then it's going to stay in the negative and just go all the way to 0. And that is what your Nike function actually looks like. So we went through distance. Now we will talk about depth. So let's draw another graph. So we'll draw this one a little bigger here so I can show more. So depth here, right? How deep your basin is of your function. Depth indicates bond strength and energy. So on your y-axis, it has EV, it is energy. And so when you're all the way at the bottom here, that's when you have the most energy, right? So we'll pretend there's like a little ball right here. And it can go across at different levels. And if you add energy, say you added heat to a material, like iron, for example. If you added heat, this atom here, it's going to start vibrating, and it's going to start jumping to different levels. And eventually, it's going to get to a point where it comes all the way out, and it's going to just leave. It's going to leave the bowl. And at that point, that is when your material has melted and your bonds are breaking apart, and it, instead of being a solid material, it is a liquid material, and you're not solid and you're not cohesive anymore. And that basically explains how the depth is very important in indicating bond strength and bond energy. We'll be going through the models that were generated for each equation. And first off, here's the aluminum graph based off of this equation that was given. And you can clearly see the Nike function, how it dips below the x-axis and then comes back up towards 0. The function for the iron graph as well, where the same can be seen for this graph. Modulus was also calculated with aluminum and iron, and Young's modulus is calculated from the slope of the original graph, which is just done by taking the first derivative. So this equation, what is the first derivative of the previous graph for aluminum, and this is the graph that was generated. Graph for iron, where I took the Young's modulus with the first derivative of the previous equation of iron, and for all these equations, these graphs, I inputted them into Desmos, and it generated a graph for me. The second derivative of the original function, and this is the graph that was created. Modulus graph for iron, where I took the second derivative of the original iron function.
All right, so the prompt for this question is to use vacancy formation energy data for aluminum and iron. Compare the concentration, aka the number of vacancies per meter cubed, and the vacancy occurrence probability / chance of finding an atom site vacant for both aluminum and iron. And additionally, answer how would this affect yield strength. The formula needed to solve this problem is this. While it may look like a seemingly simple formula, it requires a lot of variables. The variables we need in order to solve our problem are n subset v, which is the equilibrium number of the vacancies, n, which is the total number of atomic sites, which is the concentration that we're looking for, Q subset V, which is the energy required to form a vacancy, and K, the Boltzmann constant, as well as temperature, which is in Kelvin. And here's the key right here, just so everybody can see. Solve for N. N is the total number of vacancies or the concentration, as I said before. This variable can be represented with the equation N equals Z over V, with Z representing the number of atoms and V representing the volume. At the moment, we don't exactly know the volume. However, there is an equation that has a relation to volume with variables that can be easily found. That is the density of a molecule equation, which would be this right here. This is rho equals Z times the atomic weight, which is A subset E, over volume times the Avogadro's number. So with this, we can rearrange to solve for V, then plug in the original N equation, and you get this. N equals rho times Avogadro's number over the atomic weight. You see here we have the concentration values for both iron and aluminum. And here are the probabilities for both iron and aluminum. Now, what does this mean for yield strength? It means in yield strength that aluminum with a higher vacancy concentration is more susceptible to softening, especially at higher temperatures. However, iron with much lower vacancy concentration retains higher strength at elevated temperatures.